Hello, everybody. Greetings from Fukushima, Japan. My name is Alexey Konoplev. Originally, I'm Russian environmental chemist. Back in 1977, I graduated chemistry department of Moscow State University, where you are now, as I understand. So today I represent Institute of Environmental Radioactivity at Fukushima University, where I worked for last 10 years. Besides scientific research, I am giving 2 lecture courses for graduate students at our university. So they title Nuclear Disaster Studies and Environmental Radioactivity Sciences. So let me share the slides now. Can you see the slide?
Yeah.
Okay. So the title of my lecture today is Nuclear Disasters, Radioactive Contamination and its Effects on Humans and Environment. So let me briefly introduce you our institute, which was established in 2000. Just a moment, in 2013, soon after the Fukushima Daiichi nuclear power plant accident. And the objective of the institute was quite clear from the start. So to organize and carry out fundamental studies of the national and international level on behavior of Fukushima-derived radionuclides in the environment and their biological effects. So the institute is located in the Fukushima University campus. So here is the institute, 60 kilometers away from Fukushima Daiichi nuclear power plant. And of course, this is quite convenient because we have a chance on the everyday basis to go to the contaminated areas and carry out the field experimental work. Here you can see the campus of the Fukushima University. Here are 2 buildings belonging to our Institute of Environmental Radioactivity, and this is our team. It's not very large, but quite efficient. So let me start with the start of nuclear era, which was in 1945. I think, as you already know, 16 July 1945, the first nuclear bomb test, Trinity, was carried out in New Mexico. And then 2 atomic bombs were detonated over the Japanese cities of Hiroshima and Nagasaki in August 1945. By the end of 1945, the bombing had killed an estimated 140,000 people in Hiroshima and further 74,000 people in Nagasaki. In the years that followed, many of the survivors would face leukemia, cancer, or other terrible side effects from the radiation. The use of 2 relatively small nuclear weapons in 1945 have resulted in increased level of leukemia and cancers amongst atomic bomb survivors over a period of 70 years, with new illnesses and diseases expected for years to come. So, the incidence of leukemia among survivors reached a peak of 4 to 5 times that of non-exposed control group in the years following the atomic bombing, before diminishing 10 to 15 years later. The health of non-exposed children of atomic bomb survivors has been intensively followed in recent years. These are children born to so-called hibakusha, who are survivors of atomic bombing in the years following their parents' direct exposure. This second generation population includes some 200,000 persons who are currently approaching the cancer-prone age of 50, 60 years. If the radiation exposure damaged the genes of hibakusha, as it has done in animal studies, genetical transmission of radiation effects will be another long-term concern requiring years of treatment. A large-scale epidemiological study of this population is currently underway. So here you can see the map of nuclear weapon testing. Here you can see the map with the sites where nuclear weapons was tested by basic nuclear powers. First of all, United States, Soviet Union, UK, France, but further later, China, Pakistan, and India. And here you can see the distribution in time of the number of tests starting from 1945 till recent years. As you know, in 1963, nuclear powers agreed to ban the nuclear tests in atmosphere. And this was the reflection on the very high global deposition of radionuclides, fission products, as a result of atmospheric weapon testing. And here you can see the annual global strontium-90 deposition as a result of atomic testing during the years. And you can see that the maximum of deposition was in 1963. And then we had sharp decrease due to agreement between nuclear powers to stop nuclear tests in the atmosphere. So nevertheless, as you can see, this diminishing was not immediate. This is because the deposition, they come from the stratosphere, and this takes time to, let's say, to purify the stratosphere from these fine particles containing radionuclides. Okay, here you can see the classification of nuclear disasters or nuclear accidents. So, this classification is in accordance with International Nuclear and Radiological Event Scale, which was invented by IAEA. IAEA is the International Atomic Energy Agency, which is sponsoring your winter school, as I understand. So this event scale, or INES, was introduced in 1990 in order to enable prompt communication of safety significant information in case of nuclear accident. And the scale is intended to be logarithmic, similar to the moment magnitude scale for earthquakes. There are 7 non-zero levels on the INES scale, 3 incident levels and 4 accident levels. There is also a level 0. The level on the scale is determined by the highest of 3 scores. First, off-site effects. Second, on-site effects. And defense in depth degradation. So, the highest level, 7, contained the major accident. At the moment, there have been only 2 level 7 major accidents. These are Chernobyl nuclear power plant accident in 1986 and Fukushima Daiichi nuclear power plant accident in 2011. And here you can see the comparison of cesium-137 distribution deposited on the land after Chernobyl accident. And here you can see the same, in the same scale, the map of cesium-137 deposition after Fukushima Daiichi nuclear power plant accident. Of course, the area contaminated after Fukushima accident is much smaller than area after Chernobyl accident. There are 2 major reasons for that. First of all, the amount of released cesium-137 in case of Fukushima was 5.5 times lower as compared with Chernobyl. There is another reason. So the Fukushima Daiichi nuclear power plant is located on the coast of Pacific Ocean. And during the release, the wind was directed mostly towards the Pacific Ocean. Therefore, 80% of cesium-137 released by Fukushima Daiichi nuclear power plant was transported over the Pacific Ocean and deposited on the surface of Pacific Ocean, and of course diluted there significantly. And only 20% of the cesium-137 release was deposited on the land and contaminated Honshu Island, as you can see here. Okay, the next level in terms of consequences is the level 6, which is called serious accident or significant release of radioactive material likely to require implementation of planned countermeasure. To date, there has been only 1 level 6 serious accident, and this is so-called Kyshtym accident in 1957. So, however, the city Kyshtym has nothing to do with this accident. So this was the accident at Mayak, Production Association Mayak, which was located nearby to city Kyshtym. So a thermal explosion of a tank containing high-level liquid waste occurred in September 1957, creating what has been known as the Kyshtym accident. About 740 petabecquerel was actually released during the accident, but an estimated 90% settled in the immediate vicinity of the explosion site. 74 petabecquerel of radioactivity was released into atmosphere and dispersed by the wind to form the so-called East Ural radioactive trace of about 30 to 50 kilometers width and about 300 kilometers long in northeast direction from Mayak. So today we will consider three contaminated areas. Mayak area in Russia, Chernobyl nuclear power plant contaminated areas in Ukraine, Belarus, and Russia, and area contaminated as a result of Fukushima Daiichi nuclear power plant in Japan. So first, let's consider the Mayak case. Production Association Mayak is located on the South Europe, near the border between Europe and Asia. So over here. And it is situated on the upper reach of Kecha River, part of the large Kecha, Isit, Tabol, Irtysh, Ob river system, ending up in the Kara Sea of the Pacific, of the Arctic Ocean, sorry. So here you can see the map of Production Association Mayak and surrounding areas. The Mayak belongs to nowadays to Russian State Corporation on Atomic Energy, Rosatom, and is located in the northern part of Chelyabinsk region, near the town of Kyshtym, as I told you already. The enterprise was established at the end of the 40s years of the previous century to produce and process weapons-grade plutonium. Although Mayak is still engaged in military work, the production of weapons-grade plutonium ceased in 1987, and the enterprise has increasingly directed its technical potential towards non-military applications. By the middle of 1948, the first military reactor was installed. This military reactor was in operation and generated plutonium for 39 years. It was eventually shut down in 1987. Between 1949 and 1955, 5 nuclear reactors were built at the site and 2 more reactors by 1979. In 1976, a new radiochemical plant for spent civil reactor fuel was brought into operation. So here you can see the detailed map of Mayak location. So you can see health protection zone covering an area of approximately 350 square kilometers around the site. Both agricultural practice and permanent residence are forbidden within this zone, although the area is still used for research purposes. A larger area has also been designated as observation zone, where regular monitoring occurs, but where agricultural practices are permitted. Unfortunately, during the development of Mayak, a combination of major errors in judgment and technical failures caused severe environmental contamination in the vicinity of the Mayak. Major incidents are presented over here. First, direct discharge of intermediate and low-level radioactive waste to the Teche River, which was carried out starting from 1949 to 1956. Then discharges of liquid radioactive waste to Lake Karachay starting from 1951. Then we had the so-called Kishtim accident in 1957, which I mentioned already. And finally, we had a wind transport of contaminated sediments from Lake Karachay in 1967. Discharges of strontium-90 and cesium-137 that occurred during the period 1949 to 56 have contaminated about 240 square kilometers of Teche River floodplain with an area of 80 kilometers contaminated at levels above 3.7 to 10 by 4 becquerel per square meter. About 7,500 people evacuated from 20 settlements along the course of the Teche River in 1953 to 1960, received radiation doses ranging from 35 to 1,700 millisievert. Discharges of intermediate and low-level radioactive waste to Teche River between 1949 and 56 in amount more than 100 petabecquerel are now considered as a serious error in judgment. The only excuse is that experience at that time was very small and there was no clear understanding about potential consequences of such radioactive contamination for environment and people living in the area. So here you can see the Lake Karachay, which was called the most contaminated lake over the world. This reservoir was originally a small, shallow, natural lake and a tendency to dry out during drought. In the 40s, it was 750 meters long and 450 meters wide. This was a shallow lake of the depth approximately 1.5 meters. Since 1951, the lake has been used as a repository for intermediate and low-level radioactive waste, replacing the previous practice of discharging waste into the Teche River. This is because Karachay Lake is located just on the industrial side of Mayak, and therefore in closed, absolutely closed area. As you know, the Karachay Lake doesn't exist anymore. It was completely remediated, fulfilled with stones and cement blocks, and so there is no anymore Karachay, and the problem of contamination of Karachay Lake. However, the problems of groundwater contamination, the radionuclides from Lake Karachay penetrated due to the infiltration to the groundwater and seriously contaminated the groundwater. And the movement of this groundwater, furthermore, is a real problem now, and it's still this problem is still being solved. Here you can see the maps of groundwater contamination by strontium 90 and cobalt 60. These two radionuclides are the most mobile radionuclides amongst the fission products and transuranium elements. So you can see this is the Lake Karachay itself, how it was, let's say, many years ago. And here the area impacted groundwater, which is much, much bigger. And here also the similar picture for cobalt 60. So this is a still serious environmental problem, which should be solved in the close future. So now let's consider the Chernobyl accident, which happened 26 April 1986. This is the most severe nuclear accident in the history until nowadays. As a result of the Chernobyl accident, about 85 petabecquerel of cesium-137, 54 petabecquerel of cesium-134, 1,760 petabecquerel of iodine-137, 10 petabecquerel of strontium-90, and 0.07 petabecquerel of plutonium isotopes were released into the atmosphere and transported over the long distances. So the accident at Unit 4 of the Chernobyl nuclear power plant took place shortly after midnight on 26 April 1986. Prior to the accident, the reactor had been operated for many hours in non-designed configurations in preparation for an experiment on recovery of the energy in the turbine in the event of unplanned shutdown. The cause of the accident is rather complicated, but can be considered as a runaway surge in the power level that caused the water coolant to vaporize inside the reactor. This in turn caused a further increase in the power level with a resulting steam explosion and destroyed the reactor. The graphite burned for many days, and the releases of radioactive materials continued until 6th of May 1986. So, one of the most important key characteristics of any accident is the source time. Here you can see the daily release, the rate of release to the atmosphere of radioactive material, excluding noble gases, during the Chernobyl accident in exabecquerel per day. This is 10 in 18th power. So after 6th of May, the release dropped down significantly. However, during the 10 days, every day, there were substantial releases of radionuclides. Okay, and here you can see the map of cesium-137 deposition on the territory of Europe. You can see many countries were impacted by the release of Chernobyl nuclear power plant. And the shape of this trace, of Chernobyl trace, is quite unusual and unexpected. So why was that? This was because this right figure shows the changes of wind direction during the accident. As a result, radioactive materials were transported and deposited in various directions. And here you can see the first plume. Then this is the second direction. This is the third. And then fourth, fifth, and sixth. Therefore, the wind made 360 degrees turn during these 10 days. So this means that radionuclides released from Chernobyl nuclear power plant, they transported in very different directions. Moreover, important factor of forming the shape of radioactive trace are precipitation. And when the cloud pass in the atmosphere, if the cloud overlap with the precipitation, the deposition goes much faster. The wet deposition is much faster than dry deposition. And therefore, this picture also reflects where the, let's say, rains took place during the passing the cloud along with these territories. Dominant parts of radionuclides deposited on the soil surface in the Chernobyl nuclear power plant vicinity was incorporated within so-called nuclear fuel particles. Nuclear fuel means uranium dioxide or products of uranium dioxide oxidation by the atmospheric oxygen. Particles dissolution was the key process governing radionuclides mobility and bioavailability in soils during first years after the accident. Reliable prediction of the radiation situation dynamics in the Chernobyl area during these years was impossible without understanding and correct modeling of fuel particles behavior in soils and sediments. Release of fuel particles as a result of Chernobyl accident accounts for two major features in the behavior of Chernobyl origin radionuclides. First, initial mobility and availability of radionuclides in near zone was lower those observed in similar conditions in case of global fallout, Kyshtym accident, and application of isotope solutions. Deposition of fuel particles on underlying surface, primarily into near zone, led to strong dependence of the radiocesium initial mobility on the distance to damaged reactor. So, the Chernobyl nuclear power plant cooling pond, here you can see the map of the cooling pond. And nowadays, the water level of the cooling pond is drawn down because pumping of water from Pripyat River to cooling pond was stopped in 2014. So the cooling pond was used as a reservoir of cooling water for Chernobyl nuclear power plant reactor until 2000, when the plant was finally shut down and the cooling pond became no longer required for operational purposes. So then in 2014, water pumping from Pripyat River to the cooling pond was stopped. And as a result, the cooling pond began steadily declining and was reduced by more than 6 meters in the water level. By now, fuel particles, which were released by the Chernobyl nuclear power plant accident, have been almost completely disintegrated in terrestrial soil. Due to a low dissolved oxygen concentration and high pH, dissolution of fuel particles in the cooling pond sediments was significantly slower than in soil. As a result, in the cooling pond sediments, the prevailing part of strontium-90 activity occurred in the form of fuel particles. After water level drawdown, part of bottom sediment exposed for the atmospheric oxygen, which accelerated fuel particles dissolution and radionuclide remobilization. So, some information about the aftermath of the Chernobyl accident. The amount of radioactivity released during the accident was like that produced by atomic bombs. In the early phase after the accident, 28 people died of radiation sickness. Amongst the 134 confirmed radiation sickness cases, a further 11 people died in the period 1987 to 1998 from various causes, including disorders of bone marrow, which has been linked to radiation, and also heart disease and cirrhosis of the liver. Approximately 4,000 cases of thyroid cancer were observed in children and adolescents during the period to 2003. These were due to exposure to iodine 131 during the first weeks after the accident. It is clear that extremely high levels of radioactivity deposited during and shortly after the accident damaged the ecosystem in parts of 30 kilometers exclusion zone. In an area of so-called red forest, approximately 4 square kilometers, pine trees were killed shortly after the accident, and serious damage to trees was observed over a much larger area, several tens of square kilometers. Deciduous trees were much more resistant to radiation than coniferous. So in areas of very high radiation doses, damage to deciduous trees was also observed. So now let's consider shortly the Fukushima Daiichi nuclear power plant accident. So here you can see the, let's say, the timeline of the accident. Here you can see the operating Fukushima Daiichi nuclear power plant accident before 2011. As you know, in March of 2011, the Great East Japan earthquake took place, which created tsunami. And here you can see the scheme of tsunami attack on the Fukushima Daiichi nuclear power plant. Unfortunately, Fukushima Daiichi nuclear power plant was located relatively close to the epicenter of the earthquake, and the wave of tsunami was rather high, up to 15 meters height. At the same time, the anti-tsunami wall, which was constructed by KEPCO in front of Fukushima Daiichi nuclear power plant, was only 5.7 meters height, and therefore tsunami wave easily overcame this wall and flooded the site of nuclear power plant. Of course, due to the earthquake, all the power lines to the nuclear power plant were destroyed, and therefore there was no power, external power, coming to the nuclear power plant. Of course, the nuclear power plant had a diesel generator necessary for the operation of the nuclear power plant. Of course, the nuclear power plant was automatically shut down when the earthquake happened. However, the residual heating was going on, and the problem was that the diesel generator were located on the knees of the building of the nuclear power plant, and this building was not very well hermetized, and therefore this diesel generator were flooded and broken, and therefore the cooling system stopped to work, and therefore nuclear fuel lost the cooling, and as a result, 3 operating nuclear reactors were destroyed, and actually 4 units were destroyed, but because of hydrogen explosion, and their ventilation system were connected to each other. And as a result of these unfortunate events, here you can see the trace of Fukushima Daiichi nuclear power plant cesium-137 contamination, which is of course much less in terms of area as compared with Chernobyl, but still the levels of contamination are comparable. So I see that my time is coming out. So I just want
Alexei, no, it's okay. We have time.
It's okay?
Yeah,
so
it's okay.
I should not speed up.
No, okay.
We have time, yeah?
Yeah.
Okay, no problem. So, as you can see, the behavior of radionuclides in the environment is governed by 2 major factors. First factor is radionuclide speciation in the fallout and its transformation. And the second, climate and environmental characteristics determining radionuclide fate and transfer. In terms of speciation, in case of Kyshtym accident, radionuclide were released mostly in soluble forms because they were part of liquid radioactive waste. In the case of the Chernobyl accident, radiocesium was incorporated to great extent in fuel particles, which are insoluble in water. Chemical forms of radiocesium resulting from the Chernobyl accident were depending on the distance to the Chernobyl nuclear power plant, since fuel particles primarily deposited in the vicinity of the damaged reactor, and radiocesium transported over large distances was that incorporated in so-called condensation particles that are easier soluble in water. In Fukushima case, the studies have revealed spherical glassy hot particles. Here you can see the fuel particles of Chernobyl origin, and here you can see the glassy hot particles. They have a spherical shape, and these particles contain, beside radiocesium, uranium, and other elements specific to nuclear fuel and reactor materials. However, they are called cesium balls because as a rule, the majority of their activity is determined by cesium isotopes content. So these particles are also insoluble in water, and radiocesium leaching from them is even slower than from Chernobyl fuel particles. Let me say the time scale of leaching of radionuclides from Chernobyl fuel particles is about, in average, is about 2 years. The time scale of leaching of radionuclides from glassy hot particles or cesium balls in Fukushima is about 10 years, much slower process. So after the nuclear accident, contaminated catchments become a long-term source of secondary water pollution. Here you can see heavily contaminated catchments of Dnieper River and Pripyat rivers in Chernobyl. And here you can see 14 river catchments contaminated in Fukushima area. These are Abakuma River, Nida River, Ukeda River, and others. So all contaminated Fukushima rivers flow towards Pacific Ocean. Observation, understanding underlying mechanisms, and prediction of radionuclide wash-off and long-term dynamics in surface runoff and rivers is a challenge for both Chernobyl and Fukushima, because this is a long-term process of redistribution. Water is not critical media in terms of radiation protection. As a rule, the concentration of radionuclides in water is low, even in fresh water. However, the rivers, they are the major pathway of redistribution of radionuclides on the contaminated territories, because, let's say, the contaminated areas became the long-term source of the radionuclide transport along the rivers. And this is the common characteristic for Chernobyl and Fukushima. So here you can see the map of annual precipitation in Japan and its dynamics during the year. Annual precipitation in Fukushima is 2 to 3 times higher than in Chernobyl, and especially in Mayak. Generally, higher precipitation, higher air temperatures, and steep slopes in the region promote higher wash-off of radiocesium and faster natural attenuation or self-purification as compared to the Chernobyl. Here you can see the dynamics for 2 years, and you can see that the maximum distribution of precipitation during the year is quite inhomogeneous, and maximum amount of precipitation takes place during the typhoon season and also during the rainy season. So typhoon season takes place from, let's say, end of the August till October. And rainy season is late spring, start of summer. Significant flooding occurs in Fukushima Prefecture during typhoon season, usually, as I said, from mid-August to October. A very rare extreme flood occurred from 6 to 11 September in 2015 as a result of tropical storm Ito. During a 6 days period, more than 450 millimeters of precipitation fell in contaminated zone, which is about 1/3 of the annual norm in Fukushima. However, this is more than annual norm in Mayak area. Annual norm in Mayak area of precipitation is also around 400 millimeters. So during the flood of September 2015, water flows washed out unsupported sections of stream banks. Also, some landslides occurred mainly on very steep slopes. And of course, this caused tremendous redistribution of cesium-137 on the catchment and particularly on the floodplains of the rivers. This slide demonstrates the most recent example of Typhoon Hagibis, which happened in October 2019. The amount of 24-hour rainfall during Typhoon Hagibis in Fukushima contaminated area was up to 400 millimeters and higher. By the way, again, this is about annual precipitation at Mayak. And here, during Hagibis, this was fallen down during one day. So, tremendous intensity of precipitation, changing significantly the distribution of radiocesium. So here you can see, let's say, actually this is a result of prediction, but the reality was similar to that. You can see that in Fukushima area, it was predicted like something like 400 millimeters during a day. So this is the flood itself. So by the way, this is the place where my house is located. So on Abakuma River. This is Abakuma River during the Hagibis typhoon. These are surrounding areas in Fukushima Prefecture, emergency, let's say, service and so on. Of course, massive flux of contaminated sediment by the river to the ocean took place during typhoon. As shown by illustration, desorption and remobilization of radiocesium from sediments increased dissolved radiocesium concentration in local coastal waters. Essential redistribution of radiocesium on the catchment was expected and happened. So the aftermath of the Fukushima Daiichi nuclear power plant accident. So this accident resulted in a large release of radioactive material to the environment with the potential for exposing the local population to radiation. However, the affected population was largely protected against radiation exposure and no one incurred a lethal dose of radiation or a dose sufficiently large to cause early health effects such as tissue reactions, often referred to as deterministic effects. The stochastic health effects with the greater potential to be manifested after a nuclear accident is thyroid cancer among children. This is the result of preferential absorption and irradiation of the thyroid gland following the intake of radioactive iodine by injection or inhalation. Previous experience shows that the dominant route for such intake is the ingestion of contaminated milk. In the case of Fukushima Daiichi nuclear power plant accident, this route was generally prevented by implementation of controls on consumption, and the estimates of thyroid doses suggest that they were generally low. It seems, therefore, that there should not be any future increase in thyroid cancer that could be attributable to radiation exposure from the Fukushima Daiichi accident. Generally, in case of the Fukushima Daiichi accident, the inferred lifetime risk values are extremely low and well below the levels for which effects have been observed, and the hypothetical numbers of cancer cases calculated by using the risk models are small fraction of the expected number of spontaneous cases. There is little likelihood of discerning an increase in cancer due to radiation from the accident at the Fukushima Daiichi nuclear power plant in the general population or among emergency workers. To the end, I would like to recommend our book series, which is called Behavior of Radionuclides in the Environment. Two first volumes of the book have been published by Springer in 2020 and were devoted mainly to Lake Karachay at Mayak in Russia, and this is volume 1, and to Chernobyl. This is volume 2. These first two volumes we edited together with Stepan Kalmakov, who is the head of the radiochemistry division of the chemical department of Moscow State University. Volume 3 of the book is devoted to Fukushima and have been published last year. So now I end up, and thank you very much for your attention. I will be happy to answer any questions if you have some. Thank you.
Thank you. So, dear colleagues, any questions? No? Oh, yeah.
Thank you for your presentation. I just need to ask about the radiation level now in Fukushima. Is it safe? And what did you do for the environmental remediation? What steps and process did you take to clear off the radioactive environment?
Okay, thank you very much. Very good question. And yeah, just a moment. I will. Okay. Yeah, very good question. First of all, I would like to say that in case of Fukushima Daiichi nuclear power plant, all necessary measures have been taken very soon after the accident. The people were evacuated, and in terms of number of people, the similar number of people were evacuated from the contaminated area, and so they were relocated and for the long time, this was, let's say, so closed area. Then the Japanese government took tremendous remediation program, which have not been done in Chernobyl area for several reasons, because economical situation was different, but not only. Actually, the contaminated areas after Chernobyl were very large, extremely large. And of course, so people were evacuated from 30 kilometers zone in Chernobyl, and then some more settlements were also evacuated, which got the, let's say, high levels of deposition of radionuclides. But in case of Japan, so these evacuated areas were decontaminated, and decontamination techniques were very wide, starting from washing the buildings and so on, but also, let's say, a removal of top soil layer on very large areas. First of all, agricultural soils, urban soils, and so on. So they were removed. This, of course, produced a lot of radioactive waste. So any material which contain more than 8,000 becquerel per kilogram is considered in Japan as a radioactive waste. And this decontamination program, of course, produced a lot of radioactive waste. First of all, this radioactive waste was located in so-called temporal storages. So these temporal storages, they existed, let's say, from 5 to 10 years. Now all temporal storages are removed. So where the radioactive waste goes? Radioactive waste goes to intermediate storages. They are more, let's say, stable. They are more better constructed, better isolated, and so on. And the sites for this intermediate radioactive waste were selected in, let's say, areas nearby to Fukushima Daiichi nuclear power plant, which were, let's say, severely contaminated and no chance to be populated again. Again, what is the difference between Fukushima and Chernobyl? In Fukushima, so the Japanese government decided that they will populate this area again. So they will return this land again to the, let's say, living space and, let's say, to production and so on. So nowadays, part of evacuated areas, which was decontaminated and proved that the living in this area is safe, so repopulated. So as I know, not all and not many people want to go back. But there are some people who, let's say, prefer go back and they return there. But also these areas are populated with the people working in this area, let's say, participating in decontamination activity or participating in the management of this, let's say, area. But Anyway, I can say that municipalities, which even, Fukushima Daiichi nuclear power plant is located on the border of two municipalities, Futaba and Akuma. Both municipalities returned to their places, so they have offices there, they have everything there, like shops, gas station, so they have hotels, everything. So life is going on in Fukushima, and for me it's very interesting to observe, because I know how was the situation in Chernobyl and how different is in Fukushima, and so I hope these areas, they will, let's say, they will have prosperity in the future and normal living conditions. I hope I answered to your question.
Yeah, thank you. Thank you very much, Alexei. So, some more questions? No, thank you. Thank you.
Okay, it was my pleasure.
This program. Yeah.
I wish you successful end of the school. Bye-bye.
Yeah. Bye-bye.